we could start now?
Absolutely.
Okay, great. So, all right, folks, it's an incredible delight to welcome Professor Abhay Ashtekar from Penn State to deliver the Institute Research Day talk today. Professor Ashtekar is the Ivan Pugh Professor of Physics, the holder of the Eberly Chair in Physics, and the founding director emeritus of the Institute for Gravitation and the Cosmos at Penn State. In fact, before joining Penn State, he was the Erastus Franklin Holden Professor of Physics at Syracuse and Professor Chair de Gravitation at Paris 6. Ashtekar is a member of the US National Academy of Sciences and a winner of the Einstein Prize of the American Physical Society, which is given biannually for outstanding contributions to gravitational science. He's also only one of the 51 honorary fellows of the Indian Academy of Sciences, drawn from the entire community of scientists outside India. He was awarded the Senior Forschung Prize by the Alexander von Humboldt Foundation and held the Kramer's visiting chair in theoretical physics at the University of Utrecht, Netherlands. He also held a senior visiting fellowship of the British Science and Engineering Research Council and the Sir C.V. Raman Chair of the Indian Academy of Science. He was awarded Dr. Rerum Naturalium Honoris Causa by the Friedrich Schiller University at Jena, Germany in 2005, and by the Université de Marseille, France in 2010. He is the past president of the International Society for General Relativity and Gravitation and a past chair of the Division of Gravitational Physics of the American Physical Society. He served as the editor-in-chief of the General Relativity Centennial Volume commissioned by the International Society on General Relativity and Gravitation, and also several international journals in the field. As the founding director, he led the Institute for Gravitation and the Cosmos from 1993 to 2021. So with this, I humbly request Professor Ashtekar to kindly deliver his lecture celebrating Einstein's birthday today and the title. Professor Ashtekar.
Thank you, Professor. Thank you, Professor Mitra. It's a real pleasure for me to speak at this Roorkee Research Day, especially because it is coincides with Einstein's birthday, 14th of March. I myself, throughout my life, have worked on general relativity and various ideas that Einstein brought to us. And it has been a total pleasure for me. My name is therefore also intertwined with Einstein's name in various ways. And so for me, it's an honor and a pleasure to speak on this occasion. So the title of the talk is Gravity, Geometry, and the Quantum, and Physics Beyond Einstein. I mean, Einstein gave us this beautiful theory of general relativity, but I'm sure that he would actually be delighted to see people making efforts to go beyond what it gave us. The pictures here I have to do with left-hand side picture is a Kobe satellite. This is the artist's impression of the physics after the Big Bang. And this is really about a frame about quantum structure of space and time. So the organization of the talk will be as follows. Since not everybody would be familiar with general relativity, I will begin with a little bit of an introduction, and I'll tell you very, very briefly about discovery and the central idea of general relativity and how it leads to the notion of the Big Bang. And then we'll go to the second part, which has to do with beyond Einstein and quantum gravity. Why do we need such a theory? Where and when are quantum effects of gravity important? And what are the challenges that are facing us? And finally, I will give one approach, discuss one approach to quantum gravity, which is called the loop quantum gravity. I will tell you about the motivation, the kind of quantum geometry we are led to, and how the Big Bang is really replaced by a big bounce. There is no initial singularity, and what that entails for observations. So for most of us, we learn first about space, time, and gravity in school. And those ideas were introduced by Newton, and this total masterpiece, once in a many centuries masterpiece, Principia Mathematica, which was published in 1686. So this is a long time ago, but still those ideas dominate in our everyday life as well as even undergraduate physics. And so, as I just said, most of the familiar ideas come from the Newtonian paradigm. And in this paradigm, space and time are inert backdrops or a stage or an arena on which things happen. And things that happen have to do with particles and fields, the objects around you, the planets, the stars, everything else. But space and time are unaffected. They are just in the background. They're just sitting there. And gravity is a force between the massive bodies. And there is a universality about this force, and that is a total astonishing thing, namely the law which actually tells how an apple from a tree falls. It tells the apple how to fall on Earth is the same law that tells how the Earth should move in the gravitational field of the sun. The law is the same. The equations of motion are the same. What is different is only the initial condition. And therefore, this universality is really breathtaking. And that is really one of the unbelievable leap that science undertook when Newton wrote this Principia. And this paradigm really reigned for over 200 years, but it was shattered by Einstein's general relativity theory. In this theory, space and time fuse into a four-dimensional continuum. And the geometry of this continuum is a physical dynamical entity, like the chairs around you, for example, or like the planets. They are physical and dynamical entity. It can be acted upon and it reacts. This is a radical shift in the description of reality. And furthermore, this shift from Newton, the first part that I just mentioned, to Einstein is actually absolutely necessary to for when the gravitational field is very strong, for example, near the Big Bang and near the Big Bang and inside the black holes. So this is absolutely essential. And in fact, there is even a greater universality than what there was in Newton's law of gravity, because now not only is the description applicable just to the solar system, but in fact, Einstein's equation dictate even the dynamics of the universe as a whole. And now, what are the basic ideas of this theory? And the basic ideas of this theory can be summarized in a very succinct way as follows. The first is that space-time is not an inert background, but is a physical entity, as I just mentioned. And so the outrageous idea that Einstein had is that gravity is not a force, but it's a manifestation of the curved nature of the space-time geometry. Now, one might say, why is it that gravity can be encoded into the very geometry of space-time, but not other forces, like, for example, electromagnetic forces, electricity and magnetism? The reason is that geometry, like gravity, is omnipresent. Gravity cannot be switched off. Electromagnetism can be switched off. I can be in a room it can be shielded so that there are no electromagnetic fields inside, and we have such rooms in labs. But no matter where you are in the universe, gravity cannot be switched off. That is basically because we only have gravitational charge, the mass only of one side and not of two sides. And then it is also non-discriminating. By non-discriminating, I mean it acts the same way on everything. The electromagnetic force, for example, acts differently, whether the particle is charged, uncharged, or neutral. Gravity, on the other hand, acts the same way on everything. And finally, matter tells space-time how to curve. So, for example, here is a depiction on the picture on the right-hand side up here. Here is it's an artistic depiction. This is supposed to be a view of space, and this space is bent because of the sun up here in the center that you don't see. It is bent up here, and planets like the Earth move in the gravitational field of this, in the bent geometry of this space-time. And the point is that the planets are trying to go as straight as they can, but geometry itself is bent. So from Newtonian perspective, it is actually curved geometry. From Einsteinian perspective, the planets are trying to go in as straight line as possible, as in a motion that is as close to straight line as possible, namely the geodesic motion. And geometry is intertwined with matter via Einstein's equation. So if you tell me how much matter there is, then Einstein's equation tell me how curved the geometry is. And general relativity is really widely regarded as an intellectual challenge of the 20th century science. Conceptually, it displays what Francis Bacon told us, namely, he characterized the excellent beauty, the most sublime creations of human mind as there is no excellent beauty that hath not some strangeness in proportion. And general relativity has this strangeness in proportion. It's not come down. It's a strangeness because space and time itself is curved. The clocks tick at different rate, whether you are on the mountaintop or whether you are on the valley. All kinds of strange phenomena happen. You have black holes, you have got the Big Bang. And yet all these things happen in proportion. They happen in a coherent way and not in a random fashion. And therefore, this general relativity is really one of the most sublime creations of human mind. Mathematically, it is beautiful, and observationally, it has withstood the stringent tests that have ever been performed. Now, the illustrations of the revolutionary change that took place, that I would focus on this in this talk because we have only limited time, and that is cosmology. That is to say, the science that describes the large-scale structure of the universe as a whole. So now the point is the following, that Einstein's equation tells us that geometry itself is evolving. It's not inert. It reacts to matter. And basically, Einstein's equation tells us that the space-time curvature is, space-time curvature is given by is dictated by the matter, the so-called matter stress energy tensor. Let me just take a moment to say that I was told by the organizers to keep this talk at a general level, so it is accessible to all areas in science and technology. And that is why it's a very non-technical talk. I apologize to the experts who might have expected a much more technical talk up here. And now the point is that you take these Einstein's equations and you look at observations. And if I look at observations, then on the largest scales, the universe is homogeneous. That means that there is no preferred place in the universe, and it is isotropic. That means there is no preferred direction in the universe. If you like, this is the grandest realization of the Copernican principle, which was applied to the solar system by Copernicus. Now it is being applied to the universe as a whole. There is no special place and there is no special direction. If you add these symmetries to Einstein's equation, to solutions of Einstein's equation, then the solution immediately implies that the geometry must be dynamical. The geometry itself is changing in time. The universe is either contracting or expanding, and the observations say that it's actually expanding. And observations then say that if you go back in time, you'll find that there was a primordial explosion about 14 billion, 13.8 billion years ago, and universe has been expanding since then. So the Big Bang has a fascinating history because in general relativity, it is the absolute beginning of space-time. But however, it was not immediately accepted. These solutions were found first by Friedman in 21 to 24, and then were independently discovered by Lemaitre in 26 to 65. And in many ways, Lemaitre understood the physics of this solution deeper than what Friedman had at least published. But nonetheless, the idea that this Big Bang idea of these solutions remain outside the mainstream. Einstein himself did not really believe in it, and in 1928, in talking to Lemaitre, he thought the idea of universe expanding or time changing was tout à fait abominable, completely outrageous, completely something that he did distasteful for him. But then when Hubble's discovery came that the universe is actually expanding, then in 1931-32, Einstein changed his mind. So there was a lot of resistance. And in fact, as many of you know, well into the 60s, 70s, well into the 70s actually, the British cosmology school led by Fred Hoyle, Herman Bondi, Tommy Gold, was actually pushing for the idea of a steady state universe in which there is no Big Bang. But this idea of Big Bang, it therefore remained outside the mainstream until the ideas of nucleosynthesis came. I mean, our understanding of nucleosynthesis came about. The heavy elements actually that we see around us are cooked in the stars. They are the stars of the machines, the nuclear reactors in which these heavier elements are formed. But the lightest elements, their abundance cannot be explained by just this nucleosynthesis in the star. And then people realized that there must have been a very hot initial phase of the universe in which these light elements were formed up here. And therefore, this was the work of Gamow and his collaborators. And then this nucleosynthesis said that there had to be the universe was hotter in the past than it is today. And that meant that the universe is evolving. And then finally, there is a cosmic microwave background, or the CMB. This is basically the radiation that was emitted when the matter decoupled from radiation. Until then, the universe was too hot. Matter and radiation was sort of, there was a plasma. The bound states of atoms could not be formed. Once the universe cooled enough, about 380,000 years after the Big Bang, then the statement is that the matter could actually be formed. Hydrogen atoms could be formed, and then the photons got released. And these are the photons that we see with the so-called cosmic microwave background, which is absolutely everywhere around us. And the spectacular success over the last 3 decades has to do with the origin of the observed large-scale structure of the universe. Namely, there are tiny inhomogeneities in the cosmic microwave background that were actually seen by various observational missions. There were 3 major missions. The first was called COBE, the second WMAP, and the third Planck. And the Planck released its data only relatively recently in 2000, and the final data, 2018. And this has enriched our understanding very much, and we can trace back the observed large-scale structure of the universe shown in the left-hand side up here in this diagram. One can actually explain this large-scale structure of the universe starting from the tiny inhomogeneities in the universe that are captured by the cosmic microwave background when the radiation decoupled from matter. And then one might ask, what is the origin in the cosmic microwave background of this tiny inhomogeneity itself? And interestingly, one of the leading scenarios that we have today is inflation. And interestingly, in that scenario, in fact, these tiny fluctuations were seeded much earlier in the history of the universe at the onset of inflation. And that is because of the quantum fluctuations of the space-time geometry itself and the quantum fluctuations of matter in the early part of the universe up here. And the exponential expansion, which is the inflation, occurred much before this decoupling of matter and radiation. And so this really, Einstein has had a huge triumph. I told you about the cosmic microwave background, but also in astrophysics. On the right-hand side, you see gravitational lensing predicted by general relativity. On the left-hand side are the orbits of the star around the central black hole in our own galaxy. The left picture is that of 2 neutron stars which are colliding, and these collisions emit gravitational waves which are accurately predicted by general relativity, and they have been detected in the terrestrial detectors by LIGO and Virgo. And then on the right-hand side up here, you've got 2 black holes which are colliding, and there are many such events, more than 100 such events that have been seen to date. And then in the middle is really the curves which represent the motion of a binary system called the Hulse-Taylor's pulsar. This is the 2 objects. One of them is a pulsar, they're orbiting around each other. And as they do, they emit gravitational waves. And as a result, they're slightly falling towards each other, coming closer to each other. And they produce for us very accurate tests of general relativity. There is a centennial volume which was published in 2015 to celebrate Einstein's general relativity. And for those of you, particularly research students and postdocs who might be interested in understanding the current status and also historical development, conceptual development of various ideas, there are 4 parts, and these 4 parts will give you an up-to-date information about general relativity. Okay, so this is the first part. Now let me begin with the second part. Quantum gravity. Why do we need it? Where and when is it important? And the challenges. And this theory would take us beyond Einstein. So the limitations of general relativity are the following. It is a very beautiful, sublime theory. It has been accurately tested in astrophysics, but it has limitations. And they arise because it ignores the rich quantum physics. We apply general relativity to astrophysics and cosmology, and quantum physics to atoms, nuclei, and elementary particles. So it's kind of a divided, slightly schizophrenic view of looking at the universe. But near the Big Bang and inside the black hole, the most dense objects or the largest scales and the smallest scales, they come together. And then they meet, and therefore then general relativity predicts that we have got infinite matter density and curvature at the Big Bang, the smallest, in the smallest volume, we have got lots and lots of matter, so infinite matter density up here. And then the framework, Einstein's theory, just breaks down. And therefore, Einstein's theory would just predict that there is a singularity, there are infinities, and physics just stops. But this is then a strong hint that this pathology arises because we ignore quantum physics. And because quantum physics will be important at very strong densities of matter and very high curvature, which is completely ignored in general relativity. And here is an artistic impression of the Big Bang on the right-hand side picture up here. Time is running up and space is in this 2 horizontal direction. And here the universe, so to say, begins. At the moment, the universe is expanding. So we are here somewhere. And if you go back in time, then you will see that the universe is actually contracting. And then at some stage, a Big Bang occurred. So the fabric of the universe just tore. And that was the Big Bang up here. Now, the interesting thing is that people generally think of Einstein as being opposed to quantum mechanics. And it is true that he wrote criticisms of the then understanding of quantum mechanics, many of which are applicable even today, which has to do with whether quantum mechanics is complete or not. But he had a lot of respect for quantum mechanics. There's just no doubt about it. And here is sort of an example in the paper of 1916, where he first predicted that general relativity will have gravitational waves, which, as you know, has been spectacularly verified by LIGO Virgo detectors over the last 7 years. And Einstein said, nevertheless, due to the interatomic movement of electrons and atoms would have to radiate not only electromagnetic, but also gravitational energy, if only in tiny amounts. So if the atoms were described only classically, classical Maxwell theory and classical general relativity, then they would be unstable because they would be radiating this energy. As this is hardly true in nature, it appears that quantum theory would have to modify not only Maxwellian electrodynamics, not only will we need quantum electrodynamics, but we will also need a quantum theory of gravitation, a new theory of gravitation. Now, the statement is that this statement was made in 1916. That was a long, long time ago. More than 100 years have passed since Einstein said that. Then why is it that general relativity and quantum physics have not been unified even today? Now, everybody's first reaction, if you ask physicists, it is, well, I mean, there are just not enough experiments. I mean, there's no direct experimental data, or which is really, which has to do with quantum gravity. I mean, no direct ramification of quantum gravity has been observed. Already, general relativity needs quite advanced technology. By the way, maybe you know, maybe you don't know, but the global positioning satellite system does use general relativity, does use the fact that space-time is curved. The curvature on Earth is different from the curvature where the satellites are. But that really is advanced technology. And the effects of quantum theory of gravity are much smaller than those of general relativity, and therefore much smaller than what we routinely measure in the lab. And therefore, no quantum gravity effect has been measured directly. And people always say that that is the reason why quantum gravity, we do not have theory of gravity, quantum gravity. But logically, this doesn't make any sense, to me at least, because usually it is hard to construct theories for theoreticians because there are all these observational constraints that we have to fit. Now, if there are no observational constraints at all, it should be very easy to construct theories. We should be able to churn out a theory a week. Why is it that we do not have a single, consistent, complete theory of quantum gravity? And therefore, this no experimental data cannot be the whole answer. And in my view, the real answer is that to construct such a theory, we need a new syntax to describe all of fundamental physics. And that is hard. Now, why is this so? Well, in general relativity, gravity, as I just mentioned, is coded in the geometry of space-time. And therefore, quantum gravity is really, if you have a quantum theory of gravity, then it will also be a quantum theory of geometry. And geometry is general relativity is a physical entity like matter. And therefore, quantum geometry, just like matter, has atomic structure. The screen that you see in front of you looks smooth. But of course, under my electron microscope, you will see it as discrete atomic structure. So the idea is that the geometry of space and time itself should have microscopic structure, atomic structure. And then the question is, what are the atoms of geometry and how do they fit together to give us the picture of continuum under normal circumstances? Can quantum gravity provide us with equations that still hold at and beyond the Big Bang inside the black hole? Can we describe these atoms of geometry adequately with good theoretical underpinning and good mathematical equations? So this is the place where the continuum actually tears and the classical physics stops, but still, maybe using that equations that govern the atoms of geometry, we'll be able to continue physics. And what is the appropriate mathematical and conceptual syntax to describe physics if you don't have a continuum space-time geometry in the background, but this atomic structure? Or if you like, you only have probability amplitude that the space-time geometry is this or that the distance between 2 points, you cannot really measure in principle accurately. There's only a probability distribution of the results that you would obtain. If this happens, then how do you do physics? How do you make predictions? And this is really hard, and that requires a new syntax to do all of physics. And so this is the second part, and therefore now let me go to the third part of the talk, which has to do with loop quantum gravity. And this is one attempt to provide a quantum theory of gravity, and I will tell you about the motivation and then how quantum geometry arises in loop quantum gravity and what happens to the Big Bang in quantum gravity. So that is what we would like to see. So loop quantum gravity, here is a community. It is an international community with many, many countries that are represented. There are about 20 to 30,000 papers on the subject, and it's a big area. It has celebrated its 30 years, and therefore there's no wonder that there are so many papers and there are so many groups. There is an biannual conference, and it draws more than 200 people consistently over the last 30 years. So what is the quantum geometry in loop quantum gravity? Well, the hallmark of loop quantum gravity is that it retains the fusion of geometry and gravity of Einstein's, and it replaces. So because Einstein wanted to have geometry and gravity, and therefore Einstein had this syntax of mathematical language he had to use, or the syntax he had to use for describing the world was that of the Riemannian geometry, a branch of differential geometry in which there is a metric which tells you what the distance between 2 points is. It is not just the flat metric, dx squared plus dy squared plus dz squared, but it's a curved geometry, as we just saw. And this is the generalization of the flat geometry, which is the Riemannian geometry. Then we have to replace it. In loop quantum gravity, it is replaced by quantum Riemannian geometry. Not only matter, but space-time geometry itself is called mechanical at the birth. And therefore, when we need brand new mathematical and conceptual tools to do physics without a space-time continuum. And this is provided by this quantum Riemannian geometry. So here is a picture that is depicting here. Namely, the idea is that, that at the microscopic level, you really have an atomic structure. But there can be, so as depicted up here, but this atomic structure can come together. This atomic structure can be different at different places, and that gives rise to the structure. So this is an artistic impression. The structure are just those of various reptiles, but the idea is that the structures that we see in the universe, they come in the same way because the atoms, when they are just like what is happening in the real world with matter. In the matter, you see different kinds of continuum matter, and that is because the atomic structure, underlying atomic structure, is very different. So the idea is the same thing is true with the space-time geometry. The geometry near the black holes is very different from geometry around Earth, for example, and that is because these atoms are organized in very, very different way in the two cases. And the key consequences are that, in fact, the fundamental excitations of geometry or of gravity are one-dimensional. So the space-time continuum, you can literally think of as a continuum, as a piece of cloth, if you like, that is woven, is a fabric that is woven by one-dimensional excitations, one-dimensional quantum threads. And these are, therefore, these quantum threads are polymer-like, they are one-dimensional, but they actually combine together to give us the impression of this continuum in the everyday life. And the analogy I like to give is that of a shirt. If you just look at your shirt, then you will see that it's a smooth continuum. But of course, you can just look at under a microscope and you will see it is woven by one-dimensional thread. And the claim is that in loop quantum gravity, the same is true about the space-time geometry itself. And Einstein's continuum is thus a very, very much an approximation, just like your shirt is when you look at it on everyday life. But if you look at it under magnifying glass, it has atomic structure. So Einstein's continuum is only an approximation. And the examples of quantum geometry is that there really is a minimum area. In other words, if you take a two-dimensional surface and if you shrink it, then of course you can shrink it to zero, but you cannot continuously shrink it to zero. There's a minimum non-zero area that is called the area gap, and it is about 10 to the minus 66 centimeter square. So it's really very, 5.1 times Planck length squared, which is about 10 to the minus 66 centimeter square. So it's very, very tiny, but it is discrete. And it's so tiny that with our most advanced instruments, we cannot see this quantization directly. So when does quantum gravity become important? Well, there are three fundamental constants of nature that enter in quantum theory of gravity. Because it's gravity, there is G. Because it is a generalization of general relativity, which itself is a generalization of special relativity, there's a speed of light, and then there's a Planck's constant because it's quantum mechanical. The unique combination of these three, which actually have dimensions of length, and that is about 10 to the minus 33 centimeters. And that is why the quantum of area is about 10 to the minus 66 centimeters. And this sets the scale at which Einstein's continuum completely breaks down. So Planck length is extremely small. I mean, for those of you who are not used to such small numbers or large numbers, the opposite of reciprocal of it would be large number. Well, we can look at how small is a Planck length. Well, let us take a proton. Now, proton is a subatomic particle which resides in the center of the atom. So proton itself is about 10 to the minus 5. Size of the proton is about 10 to the minus 5 times the size of an atom. But let us take the proton. The proton radius divided by the Planck length is about 10 to the 20. So proton is a huge object compared to the Planck length. How big is the 10 to the 20? I mean, I think we don't have good grasp of these big numbers. So 10 to the 20 in dollars, for example, would be the Indian budget, which is about $460 billion for 2022. So it's a Indian budget for $1 billion years at the 2022 rate. So it really is a huge, huge number up here. So even the proton structure, which we probe at CERN and particle accelerators that Jim Gates was talking about, that is a huge thing compared to the Planck-Length. And we're trying to construct the theory which would be good to the Planck-Length, and that is why it is so difficult. But these effects come to the forefront when there is extremely high curvature in space-time, and that is when precisely when general relativity fails. This is near the Big Bang, and these circumstances which we cannot create on the Earth or inside the black holes. That is where general relativity fails, space-time ends, general physics comes to a halt according to general relativity, but the real physics would not come to a halt if we include quantum mechanical effects. So to go beyond general relativity, we had to use loop quantum gravity equations governing the quantum threads, the atoms, atomic structure of space-time itself, rather than Einstein's equations governing the continuum fabric of space-time. So back to the Big Bang of general relativity that I told you about. In general relativity, there's an unambiguous prediction of Big Bang, but that is where the equations of general relativity fail. What happens to the equations of loop quantum gravity at the Big Bang then? Well, they do not break down. And there is a major departure from Einstein's equation near the Big Bang. The Big Bang is replaced by a big bounce that is on the cover of this Scientific American paper, which was on loop quantum gravity. The space-time continuum of general relativity tears, but the quantum threads have precise and well-defined behavior. Quantum physics does not stop, and loop quantum gravity equations tell us that there was no Big Bang. All physical quantities remain finite, and therefore these equations enable you to evolve past the Big Bang, go to the pre-Big Bang bounce up here. At the Big Bang, in general relativity, the curvature is infinite. But here, the curvature achieves a maximum value. It is huge. It is about 10 to the 78 times the curvature of the surface of a solar mass black hole. But the important thing is that it's finite. It's not infinite. And so here is a cover story from a new scientist from Big Bang. And when this big bounce idea came up, so here is our current universe. It is expanding. If you go back in time, it contracts. According to general relativity, it will just end here. And that would be the Big Bang from which everything began. The universe shrank up here to zero volume, infinite matter density, infinite curvature. But in loop quantum gravity, the loop quantum cosmology equations do not break down. You can go back in time. Everything is finite up here. And then there is another branch of the universe up here. So when I first saw, so that's what the article begins by saying, that I remember the first time we saw the computer simulations, the solutions of Einstein's equations, quantum Einstein's equation in loop quantum gravity. And I saw that in fact, there was no Big Bang, but in fact, the universe expanded past. I was very surprised. And we decided to check and recheck the calculations because we wanted to make sure it was not some fluke of the initial conditions we chose or something else. And we checked it for about 6 months before actually publishing it in the Physical Review Letters. So then the question that we would like to ask is, what is on the other side of the Big Bang, right? So here is again the artist's depiction of the picture of the universe. Time is running up here and space is horizontal, the 2 dimensions up here. And here is a picture of the universe. The universe is up at any given time, would be given by this, and is actually expanding, up here. So if you go back in time, then it's contracting. But then the statement is that Einstein's equation fail, where there is this red region up here. Quantum effects become dominant. They overwhelm the classical attraction. There is a brand new repulsive force of quantum origin that overwhelms the usual gravitational attraction and makes the universe bounce. And the interesting thing is that as soon as, so this quantum regime exists for a little time, but the interesting thing is that as soon as the curvature falls to about 10 to the minus 4 times the Planck curvature, Einstein's equations become excellent approximation again. So again, in these huge regions that we have got up here in the past branch or the future branch, away from the region where the curvature is about 10 to the minus 4 times the Planck curvature, general relativity is an excellent approximation. But at the Big Bang, it fits. In the standard cosmological models, not only in the simplest ones, but many more complicated models, the Big Bang is actually replaced by a big bounce. The universe actually undergoes this bounce, and our post Big Bang branch is joined to our current one through this red region, which is like a quantum bridge, where quantum mechanical effects dominate over the classical effects. And the point is that in this picture, the cosmic microwave background and inflation are unaffected, are largely unaffected in the sense that everything that is predicted by this picture reproduces the observations about cosmic microwave background. And therefore, cosmic microwave background and inflation are not the proofs that Big Bang occurred. Sometimes it is claimed in popular literature that the cosmic microwave background is a signature of the Big Bang. It said that the Big Bang actually occurred. There was an initial beginning with singularity. And that is not the case, because even in this picture, where there is no Big Bang, there is a cosmic microwave background with all its observed features. In fact, there is a slight improvement, which I will now talk about. But let me just tell you that this is not completely new. We knew in astrophysics that new quantum repulsive forces can occur, and they can have effect not in just minuscule atomic and particle physics, but even in astrophysics. And there is the novel quantum force associated with the quantum matter can also combat gravity and halt gravitational collapse. In stars, if the mass of the star is less than about 3 solar masses, then we can have neutron stars. And if it's less than 1.4 solar masses, the famous Chandrasekhar limit, then we can have white dwarfs. And this leads to new and fascinating type of stars. But the important thing is that if you just have quantum matter, then the mass was bigger than 3 solar masses, then the star would still collapse. Classical gravity, according to general relativity, would still win. But according to quantum gravity, then the statement is that that's not the case. Loop quantum gravity says that even for the whole universe, where the mass is much bigger than 3 solar masses, there is actually bounce. The quantum gravity effects are important. Interestingly, already in 1945 edition of Meaning of Relativity, Einstein cautioned against attributing fundamental significance to the Big Bang. He said, one may not assume the validity of field equations at very high density of field and matter, and one may not conclude that the beginning of the expansion should be a singularity in the mathematical sense. And that is exactly what loop quantum gravity is saying. It's not a singularity. But the curious history is that just as initially there was great reluctance in accepting the notion of absolute beginning of the Big Bang, in the recent years, not very recent, but in the past many years, there has been a reluctance in giving it up. And even today, many people talk about Big Bang as if it was a physical reality, that the universe really began there and everything, the physics stops at that epoch. And in fact, everything becomes infinite. This is not the case. So, as I said, microwave background was often regarded as a signature of the Big Bang, but it occurs also in loop quantum gravity without the Big Bang. And here is a nice, small, rather short video, which is called The New Meaning of Big Bang, in which 7 of us were interviewed. And we're interviewed completely at independent locations, in the United States and Europe and various places, completely differently. And we had completely different backgrounds, but everybody said the same thing, that in their view, in fact, there was no Big Bang as a singularity, but rather now what cosmologists refer to Big Bang is a stage post-inflation where the universe was very, very hot. So after reheating, the universe was very hot, and that is the Big Bang. So it is, so to say, post-inflation, not before inflation, as in classical general relativity. And so this is a short YouTube video, and so students might like to see this. So now the last question we want to ask is, can we distinguish the Big Bang from the Big Bounce observation? And the observations of the early universe we have to do with the cosmic microwave background. And you have seen many, many times probably the picture on the left-hand side, the great success of the cosmic microwave background. But if you see here, the black dots are the experimental lines. The red curve is a theoretical standard inflation curve based on the standard Ansatz curve. The Ansatz is based on standard inflation. And of course, together with all the physics that we know, physics and astrophysics that we know and then the statement is that you find these acoustic peaks and so on. But you see that there is a great incredible agreement with the theory and experiment up here, except that at the small l's, these l's are the YLMs l's. So small l's correspond to large angular scales. So at large angular scales or small l's up here, you see that in fact the observed thing are actually suppressed compared to what the theory predicts. And so this is often called the power suppression up here. What is being plotted up here is a temperature fluctuation. So basically you look at 2 points in the sky, look at temperature at one point and temperature at another point. Because of homogeneity and isotropy, the only thing that matters is the angle theta between them. So I can take the first point at the North Pole, the second point somewhere else, and the question is, what is the angle between them? And that angle is the theta. And then the statement is that these are the correlations between temperature here and temperature here. And then, so you can take this angle theta and we can plot the power at various angle thetas up here. And what you see is that above about 60 degrees, the observed power is almost flat, is almost zero. At the very end up here, there's a contamination due to galaxies, so we should not worry about it too much. But above 60 degrees, observed power is zero. But the theoretical power is bigger. Now, sometimes it is below and sometimes it's above. That doesn't matter because the power is given by the square of this thing. And therefore, the theoretical power is substantially above what is observed, is about 6 or 7 times above what is observed. And this is really about 60 degrees system. So to summarize, the Planck data agrees with standard inflation and general relativity and astrophysics extremely well in many, many respects. But there are a few anomalies. The significance of any one of these anomalies is low. But if you put 2 or more together, then that means that we are living in a universe which is exceptional. In other words, if you take the theoretical probability distribution, and if you look at realizations of that probability distribution, then if there are 2 or more of these anomalies, say that the universe we live in is 1 in a million. So it's not that typical. And therefore, people do worry about these anomalies. And in fact, this is what the Planck team itself said. This was a 215 quote where the first results were given. And here is a 2015, and here is 2018 quote. Namely, it says that if anomalies have primordial origin, if an origin is like in the loop quantum gravity, very, very, very early universe, then their large-scale structure would suggest an explanation rooted in fundamental physics. It is worth exploring any models that might explain an anomaly, or even better, multiple anomalies with multiple anomalies naturally or with very few parameters. And that is exactly what loop quantum gravity does. This Planck suggestion is realized in a specific way in loop quantum gravity. It turns out, surprisingly, that there is an interesting interplay between the very small and the very large. The very small the very small meaning the ultraviolet. It is the modifications of general relativity in the ultraviolet that actually resolves the Big Bang singularity, and we have the big bounce. But the effect of this big bounce is to create a finite radius of curvature. In general relativity, the curvature itself blows up at the Big Bang. In loop quantum gravity, it does not blow up, it is finite. And therefore, there's also a finite radius of curvature. And if in fact, the wavelengths of the cosmic microwave background modes, if the wavelengths are larger than this curvature radius, then they actually feel the curvature, they get excited, and then you get a prediction which is different from inflation. It's a bit like my walking on Earth. My footstep is very small compared to the radius of the Earth, and therefore I don't feel the curvature. But if you take an airplane, large wavelength, then you have to take into account the curvature of Earth. Similarly here, the modes of cosmic microwave background, which are very small wavelength modes, these modes up here, small l's, they correspond to small wavelength up here. These modes don't feel the curvature, but the small L or the large angular scale, large wavelength modes feel the curvature, and therefore there is actually a difference. And then several anomalies have been alleviated in loop quantum gravity without compromising the successes of standard inflation. So this is very nice because on the one hand, one starts with incredible conceptual mathematical issues, but then one can trickle down and make contact with observations. And in particular, the standard cosmological model is described by 6 parameters. I think this is the triumph of modern science, that the large scale structure of the universe can be described if you know these 6 parameters. 2 of them have to do with primordial spectrum, that is to say what happened to us at the end of inflation. 2 of them have to do with how this disturbances propagate from the primordial times from the end of the inflation to the surface of last scattering, where the radiation decoupled with matter. And then the last 2 have to do with how the radiation then subsequently travels from the surface of last scattering to us. If you know these 6 parameters, then the standard cosmological model we have a cosmological model, and we can work out any observable effects. Now, in the standard model, everything is real given. The numbers are given here, and loop quantum gravity, the numbers are given here. 5 of these numbers differ by less than 0.4%. And that is why loop quantum gravity can really reproduce all the successes of the standard model. But the 6th one, which is called the optical depth, which tells you how long the reionization epoch lasted, that is different from the standard model by about 10%. And that is quite a big difference. So therefore, the loop quantum gravity, because the loop quantum cosmology, standard model of cosmology is different from the standard one in this one parameter. And this parameter is the least well-measured parameter of the 6. For example, between WMAP and the Planck mission, it actually changed very significantly by several orders, but like several times the value of this parameter changed up here. Basically, instead of 5 here, we have 9 in Planck. So this is the least measured parameter, and so future missions will measure it, and then we'll see if in fact it is actually slightly larger as loop quantum gravity predicts or not. The important thing for me is that there are actual predictions here. So let me summarize. General relativity is based on Einstein's outrageous idea that gravity is not a force, but a manifestation of curvature of the space-time geometry. It is a deep theory and marvelous theory. It's conceptually compact and supremely beautiful and amazingly accurate in astrophysics. But it is incomplete in a fundamental sense because it ignores quantum physics. For conceptual confluence of fundamental laws, we need an even grander, deeper theory from which general relativity and known quantum physics can emerge only as limiting cases. This is the quantum gravity theory that we seek. Loop quantum gravity elevates Einstein's outrageous idea to the quantum level. Since geometry is a physical entity like matter, loop quantum gravity focuses on its atomic structure. Through quantum geometry, it has begun to provide us a new syntax for fundamental physics. An Einstein continuum is an approximation which breaks down near the Big Bang and inside the black holes. And these singularities of general relativity have proved to be gates for physics beyond Einstein that is being explored in loop quantum gravity and also in some other approaches to quantum gravity. Loop quantum gravity does not break down, and there are no infinities at the Big Bang or at the singularities. And the Big Bang in particular is replaced by the Big Bounce. And there is a brand new physics in the Planck regime with observable consequences. In addition to conceptual and mathematical syntax, it accounts for some anomalies in the CMB observation and makes predictions for future missions. And for students and postdocs who might be here, let me just end by, let me end here first with an epilogue that what has happened is really a realization of Heisenberg's, who said a new field of experience will always lead to crystallization of a new system of scientific concepts and laws. When faced with essentially new intellectual challenges, we continually follow the example of Columbus, who possessed the courage to leave the known world in an almost insane hope of finding land again beyond the sea. That is what Einstein did, and that is what various approaches to loop quantum gravity do today. And again, for students and postdocs, I will just leave this as a last slide, where there are some references. Those who are interested can look at those references. Thank you.
Thank you so much, Professor Ashtekar. Let's have a round of applause. Thank you. Thank you. So we have a bunch of queries in the chat box. Is it okay if we take them, at least a proper subset of the same?
Oh, yeah, yes, certainly, as many as you would like to take them.
Okay, lovely. So just a moment.
Sorry.
Okay, so there's a query by Deepan Betal, and he asks, could primordial gravitational waves be a probe into the early universe?
Yes, very much so. In fact, there will be, the point is that the CMB that we see, really we see from the surface of last scattering, because before that, the universe was opaque to photons, to light, whereas primordial gravitational waves they are not, the universe is not opaque to primordial gravitational waves, because the gravitational waves interact so weakly with matter. So the fact that there was so much matter around doesn't matter. The gravitational waves can still travel, and so they will bring us into interesting signatures. And in particular, it will first of all narrow down the inflationary models that we have, but it would also, I mean, for example, they will tell us about the so-called magnetic BB polarization mode spectrum, and then loop quantum gravity again has a slightly different prediction than standard inflation, and this again will be tested by the missions which are actually upcoming to measure the primordial gravitational waves. I mean, what one measures is, of course, indirectly the primordial gravitational waves, the current missions, not directly, but nonetheless, Planck might. Okay, let me not go into that. So nonetheless, these indirect measurements of primordial gravitational waves will tell us much more information than the cosmic microwave background.
He, in fact, has a follow-up on the same theme, I guess. He asks, could primordial gravitational waves be quantized due to the quantum nature of anisotropy?
No, I think they are quantized. I mean, all the quantum, okay, this was one of the big realizations in the last 30 years, namely that the cosmological perturbations, they can be tensor modes or they can be scalar modes. They really correspond to different parts of the space-time metric, if you like. But the tensor modes represent the gravitational waves. And in fact, in the analysis of inflation, they are quantized. And it is really that this quantum, I mean, these are the seeds are really the quantum fluctuations of both the scalar modes and the tensor modes being gravitational waves of themselves. Now, the way it is normally done is one assumes that you got a continuous space-time background and one quantizes fields on that. In this case, the Friedmann-Lemaitre-Robertson-Walker background. But of course, that all completely breaks down at the Big Bang. With loop quantum gravity, what you have is a possibility of actually not doing this quantization, which does not break down at the Big Bang. You can include the Big Bang, and in fact, you can go even past of the Big Bang for this. So yes, so they are quantum mechanical in nature, and their quantum mechanical nature is very important for the whole analysis, even in standard inflation.
Fine. Gopal Yadav has a question. What was the cause of the Big Bang? If before the Big Bang there was a singularity from which the Big Bang happened, how was the singularity formed?
Right. So the whole point about the loop quantum gravity is that there is no Big Bang, right? There is no singularity. So there is no cause for the singularity. It is just that there was a phase of the universe where classical general relativity fails. So if you like, the failure of classical general relativity is what gives rise to the Big Bang. Perhaps I can give you an example from ordinary quantum mechanics. If I ignore quantum physics, and if I look at the atom, then the atom, even the hydrogen atom, cannot be stable because the electron is going around the proton, and as it is going around, it's accelerating, and therefore it's radiating electromagnetic energy. This is what Einstein's quote referred to. Is giving electromagnetic radiation, and because it's emitting electromagnetic radiation, it should spiral in and fall in the nucleus. And in fact, the atoms, this should happen very quickly, and the atoms would not be stable at all. But quantum mechanics comes into the picture, and it's because of the uncertainty principle of Heisenberg's, if you like, or various reasons. You have got to, the electron does not radiate. There are stationary orbits for the electron, and therefore the atoms are stable in quantum mechanics. Classical mechanics, they are not. So in classical mechanics or classical electrodynamics, there will be singularity very quickly when the electron falls on the proton. Whereas in quantum mechanics, that is not the case. And the same thing is true with general relativity. There is a singularity. But when you bring into account quantum physics, as in quantum cosmology, this singularity is removed. So there is no singularity.
I guess probably the question could have been rephrased with his permission, I guess, is in the following way, that in loop quantum gravity, perhaps why is the curvature, though finite, but still so large?
Fantastic. So, of course, this is a solution of Einstein's equation. And therefore, the statement is that we only deduce it by taking, there's no. Okay, so let me start from that. What we have is the following. In loop quantum gravity, instead of having a metric, we got a wave function, which has to do with the probability distribution of various metrics. And of course, the question is, what selects the particular wave function that describes our universe? What selects it? And so in loop quantum gravity, we do not have a firm answer to this question, but in loop quantum gravity, we have arrived at a proposal starting from what we know about the discreteness of geometry. Discreteness of geometry at the Planck level. From there is a specific proposal that, let me just start to say what it is. The proposal is the following: that if you look at the universe today, and you look at the surface of last scattering, we have got some radius of the universe, of the observable universe. The observable universe has certain radius. If you go back in time, then this radius shrinks. But in general relativity, it will shrink to zero volume. But in loop quantum gravity, because we got minimum, the space-time geometry is quantized, there is actually a minimum that you obtain. And therefore, these quantum considerations of our space-time geometry tell us that this ball should have already shrunk to a certain size. These kinds of considerations select for us a certain wave function of the universe. And if you use that wave function of the universe, then the statement is that if you like initial conditions which correspond to the wave function of the universe at the bounds, then the statement is that the curvature is very high. If you like, another way to say it is that the curvature is so high because the atoms of geometry are packed as densely as is allowed by loop quantum gravity. Loop quantum gravity has a particular atomic structure for geometry, and how much can you pack the atoms of geometry? The maximum of packing occurs somewhere, and that is a big bounce. So the supremum is achieved at the big bounce.
Okay, so the next question is by somebody. It's a good thing, Professor Ashtekar, you know Hindi. The name is Sasta Feynman, so I don't know that whatever that is. But the question is, you said there is no experimental data for the theory of quantum gravity. How is the state for producing such things in cold atoms experiment? How is the state for producing such things in cold atoms experiment? Yeah. Schleier lab in Stanford have done some experiments on these. That's they say.
Correct. Okay, Sasta Feynman. Okay, so I'll give you a manga Feynman answer. So the answer is the following. Uh, the word quantum gravity is used in completely different senses by different communities. Here I meant really the quantum nature of gravity itself. Often people in cold atoms and so on, they talk about quantum gravity as, they're just talking about Newtonian gravity, in fact, and not even general relativity. And the question is, can one actually see the manifestations of this, the fact that Newtonian gravity affects matter, can one see it, the manifestations of classical gravity in quantum mechanical experiments involving cold atoms? So the word is used in a somewhat different manner. Unfortunately, the word, it should have been something else. It should not be quantum gravity. It's really measurements, the Newtonian gravitational effects in quantum mechanical experiments of cold atoms is a correct description, perhaps.
Okay. So there was a question from, okay, there's a phone company mentioned the model, so I wouldn't care. So the question is, there is no space-time. How do you define that curvature at Big Bang singularity?
Very good. So what we have, it's a very similar question to asking about atomic physics, right? For example, in atomic physics, we only have wave function psi of x for the electron. And then one can still say, well, but there is a first orbital of the hydrogen atom, second orbital of the hydrogen atom, the orbits that one talks about. Well, one gets them by looking at expectation values and dispersions. So similarly, to define what we have is a quantum state of geometry, and then we got operators which correspond to curvature. And so you can take the expectation value of this operator, and if in fact the fluctuations are small, then you can consider the expectation value as being the curvature. I mean, as being a proxy for the curvature, if like an effective curvature. And that's what one does. So what one does here is exactly what one does in atomic physics.
Okay, Deepan Betal has another question. How many bounces can there be? And I guess a little extension of that of just another extension would be, does loop quantum gravity permit cyclic cosmology?
Right. So the answer here depends exactly. There's theoretically everything is possible. In other words, there can be infinitely many cyclic, infinitely many bounces, or there can be only one bounce. It depends completely on the matter content of the universe. So in this sense, the situation is not very different from classical general relativity. In classical general relativity, if the critical density in the universe is above, if the density in the universe is above a certain critical value, then the universe, the topology of the universe will be a spatial topology, that of a three-sphere, and then there will be, the universe will have many, many cycles. If the critical density is equal to or less than if the actual density is equal to or less than the critical density, then in fact, the universe is just expanding or just contracting. So in loop quantum cosmology, the same thing is true. If the critical density if the density is above the critical density, then you will have bounces. But the important thing up here is that you have many bounces, because you've got normally there's a Big Bang singularity and a Big Crunch singularity, and both of them are resolved. And therefore you have many bounces. In general relativity, strictly speaking, you don't have cyclic thing, because it really ends in singularity, and then you don't know how to begin after that singularity. You just close your eyes and continue, then you will get a cyclic model. But here the statement is that you will get cyclic model because singularities are resolved. So if the density is high, bigger than the critical density, then you will have many bounces. If the density is equal to or less than the critical density, then you would have only one bounce. And so it really depends again on the particular state of the theory that is realized in nature.
In fact, he had a follow-up on that, which said, could one get more than one universe from a bounce could more than one universe emerge from a bounce from initially one universe?
So the statement is that here the theory is predictive, and the prediction of the theory is that no, the prediction is that in fact, I mean, by universe we just mean the total everything together. I'm not talking about just the causally connected part of the universe or what is observable universe, etc., etc. So the statement is that look on, if you give me some state, say in the pre-bounce phase, then I will be able to evolve it, and there will be exactly one universe. That will be the total evolution of the universe up here. Of course, within this universe, because there is a small cosmological constant, there are cosmological horizons. In other words, there will be parts of the universe which will not be observable at all for any one given observer. So if you give me observers such as us, even if we live forever, only a fraction of that universe is can be observed. You cannot receive signals from the outside because that causes structure of the space-time. So if you want to say that in this sense, there are parts of the universe which are even in principle not accessible to observations for any one given observer, then of course different observers would see, if you like, you might say that these are different universes. That is up to you. But loop quantum gravity will give you predictions for all these observers at the same time.
I guess maybe he's also interested in asking, I don't want to put words in his mouth, but I mean, is there the possibility of having some kind of an analog of a landscape of vacua in loop quantum gravity?
Yeah, I see. Right. So I think here we do not have a landscape of vacua. Here the statement is that there is really a deterministic universe. If you give me the initial state, and if you give me landscape of initial states, then they will evolve into landscape of universes, right? So the statement up here is that no, we do not have the issues that arise in string theory. We do not have this infinite degeneracy and the swampland and so on.
Gopal Yadav has another question. Does loop quantum gravity hold only at the Planckian length? What is a master equation like the Einstein's equation in general relativity? As I see in the picture of the big bounce, big bounce forms a wormhole-like structure in space-time. Is there a relation between the two?
Okay, let me just write this like a wormhole. So there is actually, okay, as far as cosmology is concerned, there is in fact a master equation which has been written down, which is really given for the wave function of the cosmological models. They evolve. They evolve with respect to what, you would ask? Well, the evolution is relational. So basically, you have to tell me one observable, so one variable which will serve as a clock. Typically, the scalar field, like for example, the inflaton scalar field, is taken to be a clock, and the volume of the universe, the anisotropy is the universe, matter density, the universe. These are all observables which evolve with respect to that. So there's an equation in loop quantum gravity, master equation, which is, if you like, the quantum generalization of Einstein's equation, which tells us how this evolution takes place. The second thing was about that these pictures that I've been drawing up here, they might look like a wormhole in some ways. Oops, sorry. They might look like wormholes in some ways, but in fact, but what wormholes do is really, this is entire space-time, right? This is not part of a space-time. So wormholes have to do with basically a 3-dimensional slice and a 2-dimensional, a ball taken out one here and ball taken out another, and the wormhole actually joins it more efficiently than going along the sheet, if you like. Whereas here, that's not the case. This really is referring to the universe as a whole. So the notion of wormhole really doesn't apply because it is the universe as a whole.
Okay, I think that pretty much finishes. I'm actually very tempted to ask you a rather thorny issue. Based on what I've heard you say, and that is, what is the last word? And I think there's no better person to ask than you on the issue of inclusion of chiral fermions, loop quantum gravity.
Good question. Yeah, so there are papers of by Gambini and Pulin, which actually address this question about about inclusion of chiral fermions. I mean, just because there are a lot of people, but there are only about 200 people working in it, and so the work in inclusion of fermions and in general connection with the high energy theory or with the standard model of particle physics has not been followed up as much as it should be. And it is one of the drawbacks of loop quantum gravity. Namely, there should be more people working on it, but given the number of people we have, it has not been. So the basic steps have been, you would find some papers by Gambini and Pulin in which these issues are addressed. But on the other hand, detailed work has not been done.
Okay, fine. Okay, I think thanks. Thank you so much, Professor Ashtekar. So I think thank you so much for the beautiful talk and your amazing patience with all the queries. Let's have one more round of applause for Professor Ashtekar. Thank you. Thank you so much.
Okay, thank you, and bye-bye now.
Bye. Stay safe. Thank you.
You too.
Thanks. All right, folks. So that's it. I mean, we come to the end of the whole thing. And so on behalf of the Institute Research Day Committee, headed by our chair, the Dean of Academic Affairs, Professor Sharma, and this incredible team, my colleagues in the team, Sairam and Rajasekar, thank you so much, guys, especially a screw up that I inadvertently ended up doing. And thank you, everybody. I mean, we thank everybody, the team here. सत्यम जी का और शुभम जी का भी बहुत बहुत धन्यवाद. आपका धन्यवाद जिनका मैं नाम unfortunately नहीं जानता हूँ. Thanks to all the students, the incredible staff. So this is us saying adieu. Thank you. Please stay safe. And this concludes our Institute Research Day Committee, Institute Research Day celebration. And Professor Ashtekar, I just wanted to let you know that we actually are gradually trying to get into the normal mode of operation, or as close as we can. And so we are physically right now in a newly constructed lecture hall complex, therefore number 2, because there is one. And this is a room specially designed for having these interactive sessions. So this is probably in terms of lecture series, though there was a conference which was held, but in terms of an institute level lecture series dedicated to a particular event is the first. So thank you so much for kindly agreeing to be a part of this. And we could have thought of no better person celebrating Einstein in particular than Professor Ashtekar. And thank you. Thanks. So namaskar. Thanks. So, okay, folks, team, I think we can end the YouTube live and the Zoom recording now. Seems to be a good point.
Okay, Professor.
Okay, bye-bye.
Bye. So, team, can I end the meeting?
Yes, sir. Yes, sir.
Okay, and I forgot. Okay, I always do this. We have this incredible. I'm getting recorded. We have these incredible students, Lucky, Mohak, and Shubham. They're integrated MSc third year students, and they have been at least my personal rocks, and they have helped in designing the website like this, updating, and I mean they've been at it. So thank you so much, guys. So conclusively, bye-bye, and I'm ending the meeting now. I must have missed something. That's why I was calling you. Yeah, right. So I can end the meeting, or not the meeting. We continue with the meeting that gets recorded. Oh, okay. We leave the meeting. Okay.